Okay, so welcome back to this next video in which we are discussing sensitization. Okay, so we're in the process of discussing the sensitization of the gill withdrawal reflex in Aplysia californica. Okay, so we've discussed that if you deliver an electric shock to the head of an Aplysia californica sea slug, okay, then basically the gill withdrawal reflex will be sensitized. Okay, so if you drop a little bit of water onto the siphon of an Aplysia californica, the gill will contract, and basically if you deliver an electric shock, the amount of contraction you get in the gill when you drop the water onto the siphon will be greater than if you haven't delivered the electric shock, i.e. the gill withdrawal reflex will be sensitized. Okay, right. We've discussed that the reason for this is that the electric shock activates this L29 interneuron within the abdominal ganglion of the Aplysia californica, and this has an axoaxonic synapse onto the axon of the L1 sensory neuron, and releases what we'll see is serotonin onto the axon terminal of the L1 sensory neuron, and this triggers it to release a greater amount of neurotransmitter, okay, onto the L7 motor neuron, which means the L7 motor neuron fires a greater frequency of action potentials and stimulates the gill to contract more. Okay, right, so we now want to see how does the L29 neuron actually make the L1 sensory neuron release a greater amount of neurotransmitter. Okay, right, so I think before we actually discuss the pathway, it's best to see the normal pathway within neurons. So firstly, I want to discuss action potentials with you. Secondly, I want to discuss how you actually release neurotransmitter from axon terminals. So we'll begin with just a brief reminder of the action potential so that everyone's on the same page. Okay, so basically the action potential obeys the same sort of themes within neurons in Aplysia as it does neurons in humans. Okay, we wouldn't be that interested in Aplysia californica if the neurons didn't at least obey the same fundamental principles as neurons in humans. Okay, right, so basically let's talk about an action potential occurring across a cell membrane. So we'll start off with what is meant by the electrical potential difference across a cell membrane. Okay, so electrical potential is a concept from physics. Okay, it's a mathematical model to help us understand reality. Okay, and this is what you do. You ascribe to every point in three-dimensional space a real number. Okay, so it can be positive, it can be zero, it can be negative, it can be an integer, it can be a rational, it can be a non-rational, okay, an irrational number. It can be any real number, okay, so every point in three-dimensional space has this real number ascribed to it, and this real number is called the electrical potential, okay, and the units of electrical potential are volts. Okay, right, so basically, all the points within the cell, so if I just draw a little cell here, all the points within the cell, i.e. within the cytoplasm, will be in an electrical equilibrium with one another, which means that the electrical potential of all the points within the cell will be the same, okay? And we might call this the electrical potential intracellularly. So I'll put big E for electrical potential and then I for intracellularly. So if I had a little man, okay, with a machine that could measure electrical potential, he could go to any point in the cytoplasm of the cell and measure the electrical potential there, and he would get this same number. So this is the electrical potential intracellularly. Again, all the points within the extracellular fluid, those are in equilibrium with one another, okay, electrically. So they're in electrical equilibrium, and they will all have the same electrical potential. Okay, so if this little man took his machine extracellularly, he could then go anywhere and get this same number. And we'll call that big E for electrical potential, and then I'll subscript it E for extracellularly. Okay, now these two numbers are not necessarily the same. The electrical potential extracellularly is not necessarily the same as the electrical potential intracellularly. Okay, they're usually not the same. Okay, so we can develop another concept, which is the electrical potential difference across the membrane, or the voltage across the membrane. So voltage is just another name for electrical potential difference. Now, strictly speaking, we should say what direction we're going in. So strictly speaking, we should say the electrical potential from the extracellular compartment to the intracellular compartment. However, people often just drop this and just say the voltage across the membrane or the electrical potential difference across the membrane. But strictly speaking, what they mean is the electrical potential difference from extracellular to intracellular. And what this means is if a little man started extracellularly and measured electrical potential, so he's got some number on his machine, okay? He's sitting over here on this point. He's got some number on his machine, and let's say he now jumps across the membrane to this point over here, and now sits there and says update. So he presses the update button on the machine, and it will measure a new value of electrical potential, and he'll get some new number on his screen, which will be the electrical potential intracellularly. What this means, what the electrical potential difference from extracellular to intracellular means, is how much would that number on his machine change? Okay, so what's the difference if you move from extracellular to intracellular? Okay, right. So what is this answer? Well, it's the new electrical potential on his screen, which is the electrical potential intracellularly. Subtract the old electrical potential on his screen, which was the electrical potential extracellularly. That gives you how much the number has changed when he moved from extracellular to intracellular. Okay, so that is what is meant by the electrical potential difference across the cell membrane, and this is usually at around negative 65 millivolts. Okay, right, so now let's talk about an action potential, okay, which is basically a fancy orchestration of changes in the electrical potential difference across the cell membrane. So, basically, what will happen is initially some sort of sensory apparatus will detect a sensory stimulus and will cause a depolarization of the electrical potential difference across the cell membrane. Okay, so maybe this is, let's say this is a sodium channel in the membrane here, which is capable of detecting the water, okay, or something about the squirting of the water, most likely the pressure, okay. So when we squirt the water onto the siphon, basically there will be some sensory receptor in the terminal of this sensory neuron, which is capable of detecting that sensory stimulus and producing a response in the form of an electrical change for the membrane of this cell, basically. Okay, so this is some sort of sensory receptor that I'm drawing here, and basically when you deliver the stimulus, it will cause this blue receptor to open. Okay, and when it opens, what it's going to do is allow sodium ions to move through it. So, we need a little bit more information, which is what the usual concentrations of sodium and potassium are on either side of the cell membrane. Usually, the concentration of sodium on the extracellular side is around 145 millimolar, whereas the concentration of potassium extracellularly is usually around 4 millimolar. The concentration of sodium intracellularly is usually around 12 millimolar, and the concentration of potassium intracellularly is usually around 155 millimolar. So basically sodium's much higher extracellularly than it is intracellularly by about a factor of 12, and potassium is much higher intracellularly than it is extracellularly by a factor of around 40. Okay, now when we open a sodium channel, okay, and this is opened because of the sensory stimulus, then what's going to happen is sodium ions can move through this channel. Now, which direction are they going to move in? Well, the concentration gradient says that they'll move inwards. The electrical gradient, we also have to take into account the electrical gradient. The electrical gradient tells us that the electrical potential intracellularly is negative 65 millivolts compared to the electrical potential extracellularly. What that means is that the electrical potential intracellularly is lower than the electrical potential extracellularly by around 65 millivolts. Okay, now sodium ions are a positively charged cation. They prefer to be in the place where the electrical potential is lower, which in this case is the intracellular compartment, okay, and it's lower by a whole 65 millivolts. So both the concentration gradient and the electrical gradient are favouring the movement of sodium in. So as soon as you open this channel, you're going to move sodium into the cell, basically. And remember, this channel is the one that was coupled to our sensory stimulus. So the sensory stimulus is going to trigger the opening of this channel. Okay, so this is the initial thing which causes the action potential. This is the initial depolarization. Okay, right. So what will this trigger? Well, we're moving sodium ions out of the extracellular fluid and into the intracellular fluid. When we move sodium ions into the intracellular fluid, that will raise the electrical potential intracellularly, because basically if you put positive charge in an area, that increases the electrical potential of that area. So the electrical potential intracellularly is going to go up. Okay? Right. What's going to happen extracellularly? Well, we're moving positive charge out of the extracellular fluid. So positive charge made the electrical potential higher, but if we're moving it out, that means the electrical potential is going to go down. So the electrical potential extracellularly is going to go down. So what's going to happen to the electrical potential difference across the cell membrane? Well, remember, this said, how much do you change if you go from here to here? Initially, you went down 65 millivolts, but now we're taking this number down, and we're taking this number up, so the amount that you're going to have to go down if you move from here to here is going to become less. So this number is going to become less negative, and when the electrical potential difference across the cell membrane becomes less negative, that's called a depolarization. Okay, so this will cause depolarization of the electrical potential difference across the cell membrane. Now let's plot a graph of the voltage from extracellular to intracellular against time. Okay, so initially, before the sensory stimulus was given, we were cruising along at around negative 65 millivolts here, but then suddenly, when the sensory stimulus arrived at this little portion of membrane here, we've suddenly started to depolarize the electrical potential difference across the membrane because of this movement of sodium ions into the cell. Okay, now, if this gets up to negative 40 millivolts, then what will happen is it will trigger an action potential. Okay, so negative 40 millivolts is what is called threshold potential. Okay, and it's the threshold electrical potential difference that you need in order to activate the voltage-gated sodium channels. Okay, so we have another little channel here, which I'll put in here, and I'll colour this one in green. Okay, so this is a sodium channel as well, but this time it's not opened by the sensory stimulus. Instead, it's a voltage-gated sodium channel, and voltage-gated sodium channels are usually abbreviated to VGNCs for voltage-gated sodium. We're using the periodic table symbol for sodium, Na, and then channel C. Okay, so Basically, when you hit negative 40 millivolts, these voltage-gated sodium channels will go from being closed to being open. And then they are going to do the job that these sensory receptors here were doing, but they're going to do it far better, basically. So what will now happen is you'll get sodium ions moving into the cell through these voltage-gated sodium channels, okay? And this is going to depolarize the membrane even more rapidly. So you'll go from being this steep to being something like this. Okay, so you'll get a violent depolarization of the electrical potential difference across the cell membrane, and it actually gets to positive levels, so it gets to plus 40 millivolts usually. Okay, so what that means is the electrical potential intracellularly is actually greater than the electrical potential extracellularly by 40 millivolts. Okay, right. Now, the voltage-gated sodium channels don't stay open for that long. They are activated to open down here at threshold potential, but then they close very quickly. So, what happens is they stay open for a certain amount of time and then they close. But don't think that it's the voltage that's causing them to close. It's not that they close at plus 40 millivolts, it's that they close after a certain amount of time, and the amount of time that they're open for allows them to depolarize the membrane to plus 40 millivolts. So it is not the voltage that makes them close. Okay, they close after a certain amount of time. Now, that's going to stop the rapid up phase of the action potential. What's now going to happen is voltage-gated potassium channels are going to open, and these are going to have to be squished into this little gap that we've got here. Okay, so this is a voltage-gated potassium channel. Voltage-gated, and then K is for potassium, and then channel. Okay, so I'll colour in this voltage-gated potassium channel in purple here. Okay, like so. And basically, what's going to happen is when the electrical potential difference across the cell membrane reached threshold potential and you open the voltage-gated sodium channels, you actually also activated the voltage-gated potassium channels to open all the way back then. Okay, but whilst the voltage-gated sodium channels are activated to open and then open instantly, the voltage-gated potassium channels are really, really slow about opening. So they just get around to opening at the time when the voltage-gated sodium channels are actually starting to close. So at this point up here, at this sort of time here, okay, so this time here, the voltage-gated sodium channels are now closing, but the voltage-gated potassium channels have only just got around to opening. But I want to stress that they too were activated to open all the way down here, not up here. It's a common misbelief that the voltage-gated potassium channels are activated to open at plus 40 millivolts. It's not true. They're activated at a similar voltage to the voltage-gated sodium channels. It's just they take much longer to open. Now, what then happens when you open these voltage-gated potassium channels? Well, we're not dealing with sodium anymore, so we have to rethink this through. So, the concentration gradient in potassium is around 40-fold, favouring the movement of potassium out. So the concentration gradient says move potassium out. The electrical gradient then, because potassium wants to be where the electrical potential is lower. Now at the moment we're up at plus 40 millivolts, okay? So that means that the intracellular electrical potential is 40 millivolts higher than the extracellular electrical potential. So at the moment the extracellular compartment has a lower electrical potential. So at the moment both the concentration gradient and the electrical gradient are favouring the movement of potassium out. Now, potassium ions carry a positive charge, so now you're moving positive charge out of the intracellular compartment and into the extracellular compartment. Okay, so that means that the electrical potential intracellularly is now going to go down because we're moving positive charge away from the intracellular compartment, and the electrical potential extracellularly is now going to go up because we're moving positive charge into the extracellular compartment. So then when we ask what's the electrical potential difference between the extracellular and intracellular compartment, that's going to become more negative because this one's going up and this one's going down. So it's going to be starting to return back to where it was. So basically you start getting the repolarizing phase. Now you might say, well, wait a second, as soon as the electrical potential difference across the cell membrane goes back to being negative, that'll mean that the intracellular electrical potential is now lower than the extracellular electrical potential. So surely the potassium ions will now want to stay on the intracellular side. Well, you're right, the electrical gradient will now favour the movement of potassium back into the cell. However, this concentration gradient still favours the movement out. So it then becomes a conundrum. Which wins? Which is stronger? The concentration gradient says go out. The electrical gradient says go in. Which one's stronger? Who wins the battle? Okay. Well, basically the answer is the concentration gradient wins the battle. Okay. At this sort of level down here that I've drawn at the moment, where we're around at negative 15, would you say? Okay, that is not strong enough to oppose the movement of potassium out that is generated by this concentration gradient. In fact, in order to actually completely stop the movement of potassium out, you would have to take the electrical potential difference across this cell membrane down to around negative 85 millivolts. Okay, so the intracellular compartment would need to be 85 millivolts lower in electrical potential than the extracellular compartment, and then the electrical gradient pulling potassium into the cell would equal the concentration gradient, which is favouring the movement of potassium out. Then they'd be balanced. And then if you took it below this, maybe to negative 95 millivolts, then the electrical potential would win. The electrical gradient would win, and it would move potassium ions into the cell. But at anything under negative 85 millivolts, so at, for instance, negative 15 millivolts, which we were dealing with, then basically the concentration gradient is always going to be stronger than that, and you're always still going to get a movement of potassium out. So we don't need to worry about that. So it'll bring it down, 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 and then it brings it a little bit too polarized of negative 65, so you get a little bit of a dip down, and then what starts to happen is the same thing happens to the voltage-gated potassium channels as happens to the voltage-gated sodium channels. They undergo inactivation as well, and they close, and now everything returns back to where it was before. Okay, so the same channels are the leaky sodium and potassium channels, which I haven't shown here. They are open in the membrane as before, and basically they will just return this back to the equilibrium potential of negative 65 millivolts, and that's an action potential. Now, the one final thing to discuss is how does this propagate from one portion of membrane to the next. Okay, so let's say this portion of membrane, which I've just coloured in orange, is undergoing an action potential. That means it will be undergoing depolarization of the electrical potential difference across that cell membrane. Okay, so you'll be bringing in a lot of sodium ions, well, not a lot, but some sodium ions at least. There's actually, a lot of physiology professors will rant to you when you say a lot of sodium ions. You do not bring in a lot of sodium ions. It does not take that many sodium ions to depolarize the electrical potential difference of the membrane. You bring in millions, but that's not many. Not when you think of how many sodium ions would be in a mole. Okay, so you don't bring in that many sodium ions in actual fact. Okay, right. You bring in these sodium ions into the intracellular compartment, which causes the depolarization of the membrane. And basically the idea is that some of these sodium ions will spread from this portion of membrane to the neighbouring portion of membrane over here. And what will that cause? Well, it's going to cause depolarization of this neighbouring portion of membrane's electrical potential difference. Okay, and the reason is that when you bring these sodium ions into this neighbouring portion of membrane's intracellular compartment, the electrical potential of the intracellular compartment is going to be raised. Okay, whilst the electrical potential extracellularly won't change that much. Okay, so if we then ask what's the electrical potential difference across this cell membrane going to do, well, if we're bringing this one up, that means that the electrical potential difference across this cell membrane is going to become less negative, i.e. it's going to become depolarized, and this produces this first phase of the action potential here, this initial depolarization, which will take the electrical potential difference across this neighboring portion of the membrane up to the threshold potential of -40, which will then activate the voltage-gated sodium channels, and you'll then get an action potential here. And that's how the action potential propagates along the membrane, basically, from one piece to the next piece to the next piece, like so. Okay, so one portion undergoing an action potential causes the next one to undergo an action potential, causes the next one to undergo an action potential. And that concept of one piece of membrane causing an action potential in the next piece of membrane, which causes an action potential in the next piece of membrane, that's called saltatory conduction. Okay, so saltatory conduction. Right. Okay, so why were we discussing this? Oh, we were discussing this so that we can understand how axon terminals release neurotransmitter. Okay, so let's now talk about axon terminals and how they release neurotransmitter. Okay, so if we've got an axon terminal here, then what will happen is basically the action potential will propagate along the membrane and it will get into the axon terminal. Now, in the axon terminal, you have synaptic vesicles docked to the presynaptic membrane. Okay, so these little vesicles that I'm drawing here, I'm going to fill up with green dots to represent neurotransmitter. And these vesicles full of neurotransmitter, these are called synaptic vesicles. Okay, and they are held attached to the presynaptic membrane here. And this is the membrane which these synaptic vesicles will fuse with upon exocytosis, and the neurotransmitter contents will then be released into the synaptic cleft, which is the space between this axon terminal and the postsynaptic membrane, which will be over here. Okay, right. So, basically, the action potential that's propagating into the axon terminal needs to cause the release of these synaptic vesicles into the synaptic cleft, basically. How does it do this? Well, basically, you transfer this electrical signal, transduce is the better word. You transduce the electrical signal on the membrane into a calcium signal in the cytoplasm of the axon terminal. Okay, and the way you do this is by putting special voltage-gated calcium channels, VGCC, on the surface of the axon terminal membrane, and these voltage-gated calcium channels will be opened when a depolarization occurs across this portion of membrane. So when the action potential reaches this portion of membrane, you'll get a depolarization occurring at that portion of membrane, which will activate these voltage-gated calcium channels. They will then open, and they'll allow calcium to move through the pore into the cytoplasm from the extracellular fluid, and this calcium will be sprayed out over the apparatus that docks the synaptic vesicles to the presynaptic membrane, and it will cause the fusion of these presynaptic vesicles with these synaptic vesicles with the presynaptic membrane, and hence the release of the neurotransmitter into the synaptic cleft. Okay, so we've now seen the process of neurotransmitter release. What we now want to do is discuss how that neuron, that L29 neuron that was in the ganglion, the abdominal ganglion of the Aplysia californica, is going to actually increase the amount of neurotransmitter which is released by the axon terminal of this L1 sensory neuron. Okay, but we'll do that in the next video.